All right, let's talk about areas of triangles and quadrilaterals. What could be more exciting? Areas of triangles and quadrilaterals. Okay, what we're going to do here essentially is just a lot of problems based on finding areas of different kinds of shapes, funny looking shapes. We're going to get formulas for all these, and so in a way, this chapter or this section of the chapter really isn't too bad. Pretty simple stuff because it's very formulaic. If you know the formula, you can plug stuff in and simplify and get an answer. There are a few topics that force us to go back and think of things like distance formula, and that never goes away. But it's mostly just based on these formulas. Now, what I want to do, though, what I want to challenge you to do is you got to know the formulas. You got to know how to use the formulas. But I want you to get used to the idea of trying to make adding up things like area as simple as possible. I mean, we could start with the simplest possible area would be a square, right? Just the side length squared. After that, they get progressively a little bit more complicated, but none of this stuff in this section is really all that bad. There are a couple of important concepts here on this slide. The area congruence postulate. Now, this is something we'll come back to again and again. What this is saying is if two polygons are congruent, then, well, what do we know about them, first of all, if they're congruent? What did we say about that going way back to the beginning of the year? If two things are congruent, they are the same size and shape. Yeah, exactly. Same size and shape. So if they're the same size and shape, then doesn't it just stand to reason logically that they have to have the same area? Makes sense, doesn't it? Pretty intuitive. The area addition postulate. This one sounds like something you'd read in a math book. It's the area of a region is the sum of the areas of its non-overlapping parts. Yeah. Well, we can maybe summarize that a little differently. Here's how I want you to think about that. When we're adding up the area of a complicated shape, we are free to cut and rearrange as we see fit. That's fine to do, as long as when we rearrange the pieces, they don't overlap. So oftentimes it's convenient for us to take something that's a little bit, strange, and make a few choice cuts and pivot things around and move some shapes around in an attempt to try to build a shape, at least in our mind, that's easier to deal with, maybe easier to calculate an area for. Get some practice with that right away. Start off with a rectangle. I mean, that's as simple as it gets, right? We've been doing this forever. The area of a rectangle is just the length times the width, right? Or the base times the height, whatever you want to call it. No big deal. So maybe one step more difficult would be a parallelogram. Notice the formula stays the same. Okay, but you got to be careful with this. In the rectangle that we were just looking at, the base and the height are completely obvious, right? The base is what we might call the length, and the height is what we might also call the width. They're just the lengths of the sides of the rectangle, right? The long side and the short side. But when we get into a parallelogram, it's a little different. Now notice that the base is in fact the whole length of that side on the bottom, but the height is not the length of that side, is it? How would you define that height instead? And this sounds a little hokey, but I think this is a good way to start the discussion, a good way to think about all these shapes. Imagine you're taking this thing and you're setting it down on a flat, horizontal glass coffee table, and that's how we're looking at it. So if we do that, the base is the part that's resting on the flat table. What's the height? Describe it to me. What would the height measurement be here? What do you think? Not the length of that side. It's something different. It's a measurement of what? What do you think? Yes, ma'am.
The space between ends of the sides.
Sure. Okay, the space between the vertical distance, maybe we'll say, right? The perpendicular distance or the vertical distance between the base that's resting on the table and the top, which is the opposite parallel side, right? That's what the height is. So it's this vertical distance right here, isn't it? That's not given to us maybe always directly. Sometimes we have to calculate that. Okay, now I've got a challenge for you here. This is a parallelogram, sure. But can we reconfigure this thing? Can we use that cut and paste principle I just talked about to maybe rearrange this in a way where it looks instead like a rectangle? Yeah, sure, I've seen people doing this kind of thing. There's a little triangle. What if we just do this? What if we just take this little triangle right here and stick it over there instead? So now we've got that. All right. Now that's a rectangle, right? The area of a rectangle is base times height. What's the base of that rectangle? I may ask it this way, maybe. Maybe that's an obtuse question there. Is it? How is it related to? How is it related to the base of the parallelogram? Same, aren't they? Sure, they're the same. We can see it in two ways. Look at the top of the parallelogram. The top edge of the parallelogram is exactly the same as the top edge of the rectangle, isn't it? Right? The other way you can think about it is the amount that I'm cutting off of the left side of the parallelogram, I'm adding to the right side to make the rectangle. So it's all staying the same, isn't it? The base is still B, and this time the height now becomes the actual length of the short side of the rectangle, right? There's nothing intensely profound about that. The point just being that isn't it easier sometimes to just cut this thing up and make it a rectangle? Everything we do today, every single one of these shapes that we're going to talk about, the area formulas, every one of them can easily be configured as a rectangle. You think of it as a rectangle. So if you ever forget it, you can always just imagine how you build the rectangle and get the formula from that. Okay? All right. Okay, triangle, no big deal, right? We know the formula for a triangle. We've been using that for a long time. Half the base times the height. Where the height in this case, the base is the flat part that's resting on the coffee table, right? And the height is the vertical distance up to the peak, to the point of the top of the triangle, right? The top vertex. How could we relate that maybe to a rectangle? This one's a little more challenging. How can we think of that triangle as being related to some rectangle? And we can kind of see here that base times height is the area of a rectangle. This 1/2 out in front is giving me a little hint. It's telling me that this triangle right here must represent half of the total area of the rectangle we're going to build. Yes, ma'am. Okay, that's one thing we could do. One thing we could do is we could make a duplicate of this and just turn it into, this is going to be, I'm running out of room here. Let me redraw this. I could do something like this. There's our original triangle, let's say. The suggestion is, and correct me if I'm wrong, is that the suggestion? We could make a parallelogram out of it like that? Yeah, that would work. That would work fine. If we did that, notice that the height of the parallelogram, the height of the parallelogram is the same as the height of the triangle, right? And the base is the same as the base of the triangle. So that's literally just half of a parallelogram. That's one way to do it. Can we do it in terms of a rectangle? What do you think? Can we do it in terms of a rectangle? Kelly, you have an idea? So, break this into two triangles. Let's take this little one and do what? Say it again. Unfold it. Right? Let's pretend this is a piece of paper that's folded over. What if I unfold it or copy it? What do you know about those two triangles? They're congruent, aren't they? For sure. Right? Just like I unfolded the paper. Same thing here. Right? Now, what's the area of that big rectangle that we just built? Isn't that the base of the whole thing? Rectangle? Isn't that the height of the rectangle? Base times height, isn't it? But how much of that rectangle is shaded? Exactly what fraction of that rectangle is shaded? 1/2. So there you go. 1/2 of our big rectangle. Every one of these you can build in terms of a rectangle. Okay. Okay, there you can kind of see it in action. We could take this. Here's one way to do it. If we cut this, another way to think about it is if I were just to cut this guy out and stick it over there, right? Well, I guess that's the parallelogram we talked about. Yeah, we're backtracking just a bit. Okay, so let's get that. Okay, important question. Very important question here. Now, this is a parallelogram. They're telling us that's our symbol for parallelogram. You see in geometry books all the time. Find the area of parallelogram ABCD. Now this is a little bit tricky. Oops. This one's a little bit tricky. How come? Is that set up right now? If that's resting on the coffee table, first of all, what's the formula for the area of a parallelogram? Base times height. Well, there's the base, right?
Right.
That's pretty simple. Where's the height? It's not given to us directly. Yes, sir.
Where the right angle is, draw a line like where the wall is.
Okay, we could do that. Sure, we could do this. We could drop a line down right there. That makes that a right triangle, doesn't it? Right. Now, this is still a little bit. We could make this work. This is still a little bit complicated, though, because we don't know directly. We know that the hypotenuse of this right triangle is 16, but we don't know how big that leg is, right? We could do some figuring, and yes, suggestion?
What if you just took BC and then like right off the bottom and made it to the right?
BCE. So take this triangle right here,
Yeah, and
cut it off, and put it right down here. That would work too, wouldn't it? Sure, we could do that. We could cut this thing, cut and paste, and turn it into a rectangle, and probably have a better chance of figuring out. Then we'd have a 9 by 16, wouldn't we? That would work. That would work. And that's a great idea. Is there a way that we could maybe avoid even having to do that by using a simple rule that we can always do? You always have the freedom when you're faced with a geometric shape like this to pick it up and reconfigure it. You could set it down on a coffee table in a different arrangement if you want to. I could reconfigure it. I could twist it, for example. Is there a better way to maybe set this down so we could get the area directly big? Put that away, please. Is there a way we could, maybe a preferable way to set this thing on the coffee table? Yeah. How about if we put AB? That's supposed to be an A right there. Whoops. How about if we put AB on the bottom? Make that the base. All right, what's going to happen if we do that? Let's see what we get. So now we end up with kind of like that, where, let's see, this would now be A, that's B. Does everybody agree if I take this thing and just kind of tip it over like that, that's what I get? A, B, then the C is, there's our C, there's D. And now we know that this line that goes from B and connects to CD perpendicularly, it's arranged vertically, isn't it? Right? So now we know that this distance right here, which is 16, and this distance right here, which is 9, that helps us out, doesn't it? Right? We can see now that the base, when we configure it like this, the base is just 16, and the height is just 9, so the area is just 16 times 9, 144. See how that works? You don't have to do anything. Just twist it. You don't even really have to physically do it. You can just kind of almost tilt your head and look at it that way. So that's the base, right? Make sense? Okay, another good, simple, but good trick. Oops. Okay, what about this? Now, if we want to, what if we're told here that we've got a triangle, and we know that the area of the triangle is 12 and the length is 6. Length of the base is 6. We want to find the height. What do we do? Where should we probably start with this problem? We could draw a triangle if we wanted to. I'll draw a triangle for you if you'd like. Whoops, it's not a triangle. There's a triangle. So we know the area is 12, the base is 6. Find the height. What do we do? Let's start with the formula. The formula for the area of a triangle we know is 1/2 base times height. Now, what's the stuff we know? Well, we know area, we know base, we're trying to find height. So the thing that we're trying to find, we just want to isolate that. We want to take the original equation and come up with a different formula where we're solving for h. Now, what are the two things we'd have to do to get the h by itself? How do I undo multiplying the right side by 1/2? I could divide by 1/2, or maybe even a little better, I could multiply by the reciprocal too. If we want to get rid of a fraction, the easiest thing to do is multiply both sides by the reciprocal. So that's good. The 1/2 and the 2 multiply to 1, so they cancel. That's good. What about the b? How do I undo multiplying by b? Yeah, divide. Well, divide. These go away. Good. So we got it. So h then now is by itself. It equals 2a over b, and I know those values. A is 12 and b is 6. So if I plug those numbers in, I just get 2 times 12 is what, 24? Divided by 6 is what? 4. So the height is 4. Right? Make sense? Okay. Okay. Trapezoids. All right. We have a formula for a trapezoid. We actually, I think, even mentioned this earlier in the chapter. Here it is. The area of a trapezoid is equal to 1/2 times the height times the sum of the two bases. I think that's a pretty clumsy way to write the formula, though. There's a better way in my mind to do it. Now, we'll come up with that better way, but let's see, first of all, same challenge as before. Can we rewrite this in terms of maybe reconfigure this so it looks like a rectangle? Draw your attention to one thing, though. What did we call this segment for a trapezoid that connected the midpoints of both legs? What did we call that? Do you remember? We gave it a name. Remember that? Mid-segment? Maybe remember that. Okay, that was the mid-segment. Now, what did we say about the length of the mid-segment? Halfway in between the two bases. It was the average of the two, wasn't it? Good, good. So the length of the mid-segment was just the average of the two bases. And we think of a way that we might be able to reconfigure this into a rectangle. 2 cuts and readjust 2 of the puzzle pieces. Yes, ma'am.
So you can cut down the mix.
Okay, so starting right there, okay, and then just go straight down. What if I do that? I create this little triangle down here. Now let's just pivot him up into place. You like it? See what I'm saying? Okay, over here, same thing. Start right there, cut straight down, pivot this guy up right there. That's what we got. Okay, now if we, let's see here, let's try something here. do this. Oops. Wrong shape. So if I look now at that, how can that change? That's weird. Can that just change a little bit? Is it just me? There we go. Okay. So there's our new rectangle. What is the height of that rectangle? What do you think? Just the same age as before? Agreed? Now, what's the length of that rectangle? Is that the same as what used to be the mid segment that went from right there to right there? Right? We said the mid segment was the average of the two bases, so there it is. Right? This distance right here is just, is just B1 plus B2 over 2, isn't it? That's the average of the two bases. So really, that's a better way to think of the area. The area of a trapezoid is just the average of the bases. So B1 plus B2 all over 2 times the height, because now it's a rectangle. Voila, how about that? Okay. Make sense? Okay. Okay, what about kite? Okay, we have a formula for kites and rhombuses. They share the same area formula. The area of a kite or a rhombus is just equal to 1/2 the product of the diagonals. Maybe let's draw those diagonals in so we can see them a little better. So here's one of our diagonals. Right there. And here's the other. Right there. Yeah.
Can I go to the restroom?
Yep. Go ahead. So we'll call this one D1. We'll call this one D2. So scoot him over where we're supposed to be. Okay. Now what? So the product of those two. Kind of struggling today. There we go. Okay, so the product of those two diagonals then gives us something, not the area of the kite, but something else. I suppose that would be, can I transform this kite into a rectangle? And look at this. If I can, whatever area we're calculating from the product of the diagonals, we seem to be half of that. So if we could build a rectangle that's twice as big as the kite.
Take the bottom large triangle on top of the top one, the smaller one.
Ah, there's an idea. There's one way to do it. Now that one hasn't come up yet. We could take this bottom one and just scoot it up here. Right? Take this bottom one and scoot it up here. And then I've just got this skinny rectangle on the top. Now what's the area of that skinny rectangle? D1 times that distance right there is only half of the whole diagonal of the kite, isn't it? Does that make sense? So I've got half of D2 times all of D1 is just 1/2 times D1 times D2. That's a good way. I like that. That's a new one. Yeah, that's one way to do it. Anybody see a different way? Anybody see a different way to create a rectangle out of this? Can I unfold some triangles? What if I take each of these 4 right triangles and unfold them to make rectangles? Now that big blue rectangle has dimensions of D1 by D2, base times height, doesn't it? Okay. how much of that big blue rectangle is represented by our original height? Exactly what fraction? 1/2, right? Because we just doubled all of the triangles to make the rectangle. Does that make sense? So it's half of the big rectangle with those dimensions. Always works, doesn't it? Okay. Same thing for a rhombus. The last thing I want to maybe show you is, let's take one example like this. What if we've got a rhombus and we're given, well, I'm not rhombus, a trapezoid, maybe. It looks like a trapezoid. We could verify it. That's sitting in the xy plane so that we know the coordinates of the vertices. Okay, so then, well, actually, I guess they tell us it's a trapezoid, so we don't have to verify it. How could we verify it, though? How could we verify that this shape is indeed a trapezoid? What's the definition of a trapezoid? How many parallel sides? Exactly one. So if I calculated slopes of all the sides, I should find that 2 of the sides have the same slope. Right? And we would. What would the slope of this, just without even kind of doing the calculation in your head, what would the slope of this bottom of the base of this thing be? XW. If the x coordinate is changing from 1 up to 8, and the y coordinate is 1 both times. 0. See the sign for 0. 1 minus 1 on the top, right? I'm going to get 1 minus 1 is 0 over 8 minus 1. I'd get a slope of 0 over 7, but 0 divided by any number is just 0. Now, we should expect that because it seems to be horizontal, doesn't it? Okay? All right, so if we want to calculate the area of this thing, this trapezoid then, we just need to know the lengths of the bases. So we're going to average the 2 bases, and we need to know the height. These are really easy distances to calculate. If the y-coordinate is staying the same, all of the change between those points is change in x, right? So what is it? What's the length of that bottom side? If it's going from x equals 1, y equals 1, to x equals 8, y equals 1. 7, sure. The y is not changing at all, but the x is changing by 7. What about the top? Y coordinate staying the same. It's 5 the whole time, but the x coordinate's changing from 2 to 5. 3. And then the height. Notice that when I go from the bottom of this, at the bottom edge of this trapezoid, y is equal to 1. At the top edge, y is always equal to 5. So what's the height? If the y values are changing by 4, sure, it's just 4, isn't it? Right? That's how much the y values are changing from the bottom horizontal base to the top horizontal base, right? So then we can do this with that new formula for a trapezoid. We can do this in our head. The area of a trapezoid is the average base length times the height. What's the average base length? Average means middle. It's the middle of 3 and 7. 5 times the height, 4. 20. Right? We're done. That's it. Okay? No big deal. Okay, how would we do this? We won't do it. Just tell me how we would. We want to find the total area of this complicated roof shape. But they tell us some things. They tell us that G, H, and K, those shapes, are trapezoids, and J is a triangle. And the roof is symmetrical, so the back side is just a mirror image of the front side. And the left and the right are the same. Thank you. So how could we do this? How could we find this complicated? It looks really three-dimensional, complicated. How could we find this total area, roof area? Sure. Yeah, sure. The moral of the story here, and it's not like it's that big a deal, the moral of the story is we could just cut this thing along all the edges and take all the flat surfaces off, set them down, and calculate the areas individually, add them up. And we know they come in pairs, don't we? We know that we've got this front piece and then a piece on the back that's just like it, so we could double this area. We got this piece and a piece on the other side just like it, right? So we could make this a lot easier than all this. right? Okay, let's try